So welcome back, guys. We continue with 3.5, matrix completion and compressed sensing. And if you remember, last time we stopped just after these kind of examples. So the main idea was to find a way, or the best way, to complete the missing data in a matrix. So, for example, we gave the idea that one way to complete these matrices is to make them with the lowest rank possible here, which is going to be 1. So, for example, for matrix A0, we can allow any multiple of 1, 2 in the second row, which means we can put, for example, 1, 2 to 4. This way, we're going to have a rank 1 matrix when completed. For B0, we can place, if we have 2 values to put here, we can put any B and C such that B times C equals 4. That way, we would have also a rank 1 matrix B0. And for C0, it allows only 6 in its last entry if you wish to obtain a rank 1 matrix. So from now on, we kind of just continue. So the main idea is to do what? To find a new matrix that minimizes some kind of norm. Okay. So with vectors, when we were about to fill in vectors, in fact, we relaxed the sparsity norm, which is the 0 norm, to the L1 norm, V1. So with matrices, we relax the sparsity norm, the norm 0, to use what we call the nuclear norm. Remember, we've seen this kind of norms previously. And in fact, this norm is the L1 norm of the diagonal capital C. So in fact, we are minimizing, at the end of the day, the sum of these singular values. So we end up minimizing the nuclear norm of A, which is the sum of singular values, okay, from sigma 1 to sigma r. So we do now have what we call a convex norm, but not strictly convex, because it's possible you may have that the norm of B1 plus B2, the nuclear norm, is equal to the nuclear norm of B1 plus the nuclear norm of B2, which is possible in the triangle inequality. So in fact, the example B0 could be completed symmetrically by any B and C between -2 and 2, and you still can have a rank 1 matrix. And the nuclear norm in that case stays at 5. So in the Netflix competition, for instance, there was a famous example for matrix completion, where the ratings of M movies by N viewers went into the matrix A0. And of course, not all the customers have seen all the movies. So the competition was to find the best way to complete the missing data. So it has, because once you are able to complete the missing data, you would be able to finalize the way your recommender system works. So the nuclear norm gave, in fact, in that case, a good solution that needed to be just adjusted for human psychology. Okay, so just a little bit of human touch to make it, in fact, work perfectly. There was a second example where we had to compute covariances on missing data. So now we have a new kind of material. We have to raise some questions on algorithms for matrix completion. Okay, so it's not a question. Here we do the mathematics preliminaries to define what we call, in fact, sophisticated algorithms to do this work of math. Okay? So the mathematical question is, so by knowing K entries, capital K entries in an n by n matrix of rank R, can we expect a perfect recovery of the whole matrix? So in fact, the magic happens is that yes, you can say yes, you can complete a matrix. So in fact, can this end rect? Prove that if this capital K is larger than C times n to the power 5 over 4 times R log n, then with high probability, the recovery of A is perfect. And to do so, in fact, they use what we call a model for random matrices A. and choose U and V as random orthogonal matrices. And you see that the idea came, the inspiration came directly from this SVD, the famous SVD decomposition. That's why, if you remember, we said that SVDs are, a core thing in this data science course. So we need, in fact, another that completes the matrix A with fixed entries which are known. So suppose you have some missing entries, but you have some which are known. That's why you have to complete the missing entries in the A which is known. In fact, in a paper by Hastie and A, which is quite recent if you think of it, 2014, they traced the development of 3 alternating iterations, each new method improving on the previous algorithm. So in the following, we will give the main ideas of these 3 iteration methods. First of all, there was the paper of Mazumder and al. In 2004, which defined what we call a soft threshold to the SVD of AK. So basically, at every iteration, they write the SVD decomposition for A and B, okay, where B is equal to UK S lambda of sigma K VKT. What is S lambda of sigma? In fact, this should be sigma, which is the maximum for every sigma. It's the maximum value between sigma minus lambda and Z. So S lambda, in fact, sets the smallest or the smaller singular values of K to 0, reducing its rank this way. Then the AK plus 1, which is going to be used in the next iteration, would minimize what the Frobenius norm of A minus BK to the square. So it's kind of minimizing the difference between your forecasting on the known part of A. Okay? So you are computing a new matrix B index K at every iteration, and on the known values, you are minimizing the Frobenius norm to the square, plus some kind of penalty, which is lambda times BK, and it's the norm, the nuclear norm of BK. So this method by Mazumder et al. In fact has a drawback, which is that the task of computing the SVD here, the first part, is quite important. It takes some time at each step. So in fact, for example, in the Netflix competition, they had how many entries? It had 8 times 10 to the power 9, which is quite huge. But in fact, it wasn't applied to the Netflix competition in the Netflix competition, but the others somehow succeeded to reduce this heavy cost, and each previous SVD gives, in fact, a warm start to the next one. So they're using the previous SVDs in the next one. Okay, so they tweaked a little bit the algorithm to work much better. And the next development, which is in fact an MIT thesis by Cerebro in his advisors, the paper actually appeared in 2005. They wrote the solution as, in fact, a CR factorization. So instead of working on B, they worked on B equals CR. Okay? That's why seeing factorization previously was quite important. So C is M by R, and R is R by M. So in fact, they wanted to find the C and R such that this objective is minimized. What is the objective? There are 2 main parts. Forget about the part in the box right now. Let's focus on the first part. The first part is kind of just exactly the same one as used by Mazumder et al., which is A minus CRT. So this is like B to me on the known part, and you are working on minimizing the norm of this, the norm squared, or the Frobenius norm squared. Okay, between on the known parts. Then you are adding the penalty, which is that the lambda over 2 kind of this is a kind of Lagrangian multiplier if you think about it. Lambda over 2 times the Frobenius norm squared of C. This is R, should have been R. Plus the Frobenius norm squared of R is also part of the objective. So in fact, it became a convex problem in C alone and in R alone, if you think of it. So it is kind of B convex. And of course, an alternating algorithm in that case will work on updating C and then updating R. Alternating vice versa, as we've seen in the other kind of algorithms we work before. In fact, each problem is a kind of ridge regression for each column of C and then each column of R. And this algorithm was called the maximum margin factorization. This produces a maximum margin factorization, CR. Okay? So this is for the cerebro-AL contribution. Now the last one, which is the most important, which is more recent, the paper appeared in 2014. It is a variation on the Mazumder method, but in fact it uses the idea also proposed by Cerebro. It alternates between C and R in the second part. So now the minimization would include all entries of A minus CR, not only those in the known positions. Okay? And in fact, this greatly simplified the least squares problem to work with full columns, both known and unknown entries, which is more intuitive, more natural to work on all kinds. So we start with this alternating least squares problem when A is fully known. Okay, so now it looks like exactly the same problem as we had previously. This is again the same mistake. And A minus CRT, working on minimizing half of A minus CRT Frobenius norm to the square, plus lambda 2 times the Frobenius norm to the square of C, plus the Frobenius norm to the square of R. And in fact, you get an explicit solution, which writes C equals to UR S lambda sigma R to the power half, and you have also an explicit value for R. And all the solutions would have CRT equal to UR S lambda sigma R and VRT, which is called the SVD of A. Okay? So just to give you the main steps of the algorithm. So in fact, the Hastie algorithm found used what we call the soft thresholding S lambda, and showed the effect of the penalty term in the previous equation. So amazingly and beautifully, that product, in fact, B equals CRT, solved this rank R nuclear norm problem. In fact, you ended up solving a smaller problem. And this connection between this objective 8 and the previous objective 7 yields the following fast alternating computation, which is B equal to CRT. So in fact, the Hastie algorithm combined the two previous works and made the algorithm much more efficient. So for the moment, so if you assume that A are known and none missing, then C is random with M by R and D equals to IR, and you can initialize and each step updates R, C, and D. So these are the main steps of the algorithm, and you can start iterating. So first of all, you try to find the R that minimizes this objective. Now, C is fixed. It has been pre-initialized. So we're working on this part of the biconvex problem. Okay, so you try to minimize this objective. So now once you find the R, you compute the SVD. D was initialized to the IR. Okay? So, and you set now the updated D to be equal to the square root of the sigma, and you update the R, which is equal to the VD. So once you get these, you minimize to find the corresponding C, so you alternate, which minimize kind of the same objective, but here now the C, the Frobenius norm is added instead of the of C instead of the Frobenius norm of R. And you compute the SVD also on CD. This should have been, and you update the D and you update the C. So you would repeat those steps until CRT converges to the solution B. And you return to the real problem in which A has missing entries and not known. In fact, this produced a very efficient sparse plus row rank representation, which could be simply written as A, which is equal to A known, plus CRT on the unknown, or in a different form. And you have, in fact, the closest form solutions for RT and CT from these objectives at the end. Okay? So you can already compute. So this is the last part I wanted to show you on 3.5, and this is closes section 3.5, and by the same time it closes chapter 3. Okay, so hopefully next time we'll see an application of this. Okay, I'll stop the recording now to continue on a couple of announcements.